Is it audible?
Yes, sir.
So we will start the session today with the continuation of whatever we discussed in the last class. Do you have any other program is scheduled now? Only very less people are there.
No, sir.
Okay, let's start another 1 or 2 minutes. Okay, we will start, I think. It's 11:30. In the last class, we have discussed about how we can able to implement if construct, if else construct in the program. Am I audible?
Yes, sir.
So we have seen that there is a powerful instruction provided in the assembly language of almost all the controllers in the processor, which is used generally to implement the if construct. So that instruction is called CMP instruction, compare instruction. You can also implement using a subtract also, but compare is more suitable for implementing the if. So whenever compare is combined with a branch instruction, conditional branching means branch in a particular condition. Branch for equality, branch for less than, branch for greater, branch for not equality. So combining compare with a branch instruction is the secret, is the concept behind implementing the if structures in assembly language programming. Today we will see that how we can implement the for loops in an assembly language. Let's take an example of a for loop. So now if I say for I is equal to 0, I less than 5, let's say I plus plus. Let's implement a small program for adding the first 5 natural numbers. So if this is my for loop, then so inside the for loop, I would have written this logic. So what is my logic? So logic would be, so I will have a variable called sum, let's say. So sum is equal to sum plus I. So this is my logic for implementing the first 5 natural numbers. So 0 plus 1 plus 2 plus 3 plus 4 will be adding the numbers. So my answer will be, so 0 plus 1 plus 2 plus 3 plus 4. This is my answer. That is equivalent to 3, 6, 10. That is A. So 0x, A is my answer. 0x is my answer. Now, I want to implement this logic in assembly language. So what are the concepts required we have to understand to implement this type of loops in an assembly language? Because there is no constructs are available. You have to implement these constructs yourself using the set of instructions provided by the manufacturer of the microcontroller or the microprocessor. Now, so let's start understanding the implementation of these for loops. If you understand the basics of one program properly, the looping, I think any of the assembly language programs you can do yourself. Because now we already know that if and else. Now the most commonly used construct in building your logics is the loop logic. So let's understand how do we build it. Now, so we can build the program always with the 4 blocks will be there. One is called initialization. I'll call it initialization. So initialization is the first block of your code. Because any loops you take it, there are certain initializations required. That is why initialization block is required. So then you have a block to perform the operation. Whatever the logic you put inside is called as an operation. It can be 1 statement, 2 statement, or a set of statements. So second block will be there. Then, so get ready for the next operation. Get ready for next operation. I can call as updations. You can call as updation, update the variables. So you can call as a updation. So what is the meaning of updation? That is before you start repeat the loop again, you have to do certain updations. That means that you may increment I plus variable, or if you have 2, 3 variables, you have to one, you have to decrement, or you have to increment, all those things you have to do it. So this is called updation. In case of an assembly, one of the job is if you are using a memory, you may be required to update your memory pointer so that you can able to fetch the next data. So updation include updating the variables, either decrementing or incrementing, and also updating the pointers. The fourth one, the fourth operation, what we are going to do is check for loop counter. Check for loop counter. The flip loop. Is it over? That means that so loop completion. So what you are checking for? So loop completion. So in the sense, if you have designed this program to work for 5 times, so check for whether it is completed or still you have to do it. So if no, means you have to continue this operation. How do you check? So here is a logic. That is you are going to check it. Yes or no? That is you are implementing. So if structure here inside that. So if I is less than 5, you are continuing it. So any loop, if you closely observe any loop, to implement that loop in a very low level language using assembly instruction, if you break down the loop concept, it basically consists of 4 operations. So one is initialization, second is an operation, the third is updating the variables and the pointers, the fourth is update the loop, in the sense loop variable, and check whether the loop is required or loop is completed. So when we write a program, keep in mind these 4 operations and write the program it is very easy to implement your logics. Otherwise, what will happen? You may not have done updation. You would have gone directly for this. Most of the times, this is the mistake. You don't update the pointers as variables properly. Then what will happen? The program indefinitely goes into the loop. So now, we will apply this logic now to this program and see that can I be able to implement for loop for the above required the program. Now I'll start with the first initialization. Now here, whenever we implement any logics, as I said always, what are my variables? Registers are my variables. How many registers I have? R0 to R12. Even you can use a stack pointer also, R13 also, since you're not using for most of the logics. Even if you are not implementing the procedures, up to R0 to R14 you can go for it. That means that around 15 registers are available to implement your variables. So that's good enough to implement most of the logics. You don't require to go to the memory to set up the variables. now initialization. What are the initialization required here? Now I require here in this case, so one variable to keep the sum, I require one variable so to set up the loop, the loop. So in this case, now what I'll do is, since I require one variable to hold my answer, so I will declare that variable, let's say R2. I will leave one R0, R1 in the beginning, so that if the pointers are required, I can use those variables R2, and I will initialize the R2 to 0. So I am using this variable, so variable to hold the sum, the sum. So it is nothing but a sum variable. So R2 I'm using is what? R2 is a sum for me. Next, since I require to generate a number from 0 to 5, I require one variable which can generate that number. So that, let's say move, I'll say R3, so #0. Now what I'll do is this variable generates a number. So variable, so for natural number, variable for natural number generation. So to start with the 0, then you have to make it 1, then you have to make it 2, 3, 4, like this you have to make it in this case. Now, now I require one loop variable which says that how many times I have to repeat it. In this program, since R3 can also be used as a loop variable, look at here, the same variable what I'm using in the logic, same variable I can use for looping also. That means that I don't require extra variable in this case, in this particular logic, so that I'll use the same thing only. So now my initialization has been completed. Now I have to go for operation. So what is my operation now? I have to add the number. So I have to add the number, what that is called as I, which is nothing but so R3 to the R2. So add R2 comma R3. Now what we'll do it? So this is nothing but what? Sum is equal to sum plus I. I have done it, sum plus I. So whenever you write in a 2-register format, always remember that R2 plus R3 will be stored in the R2 only, or explicitly you can write like this also. Both the meaning is same thing. So R2 plus R3 will be added and the answer is stored in a R2. So now what I'm doing is I will be storing my answer in R2. Now my operation is over. Now what should I do? Now I have to updation, get ready for the next operation. So in this case, what is a get ready for the next operation? That means that I have to do what is called I++. So what is an I++ variable here? So I++ variable is an R3. So I will say at R3 #1. So I've added R3 with a 1. So this is equivalent to what? R3 is equal to R3 plus 1. So this is equivalent to R3 equals R3 plus 1. So now what I'm doing is, now I have finished my updation. So I want to now check whether the loop is completed, whether all the operations has been completed. So how many times I have to repeat the operation? 5 times. So which is a variable I have to check it? As I said, the I variable, which can also be used as a loop variable also and for the logic implementation also. I will check whether I variable is nothing but so R3 has reached 5 value. This is my if logic. I'm implementing here what logic? I'm implementing my if logic here. So now always I said if is nothing but a combination of two instructions, compare plus branch. So immediately after the compare, what you have to write? Branch. When I write a branch, you have to write a condition here. So what condition? I choose not equal here. So how do you read this one? How do you read this combination of these two instructions? First read the B, branch. If, go to the next instruction, if R3, come back here, not equal to 5. So always you have to read in 4 steps. First read the B, branch. Go back to the comparison. If R3, come back here, not equal to R5. So then you write the whatever the loop, what is the label you require, continuation. Always very important the way you read this is very important. You have to read in 4 steps. First B, then R3, then NE, then the next number, then the label. So 5 components are there in that. So branch, if R3 not equal to 5, then go to the label called continue. Where is the label? Always at the operation. You have to put this always at the operation. So it's very important in a low level. One of the common mistake you do in implementing the logic is where do you put the label? If you put the label immediately after that, it will not work. If you put it before the add, that is at the move instruction, it will not work. Exactly at the beginning of the operation, you have to put it. Not into the anywhere into the initialization. Exactly at the beginning of the operation, you have to put it. Now my loop is completed. Look at this. This is my for loop. The whole logic is nothing but implements what logic now here. It's a for loop here. So what are how many variables I've used? 2 variables I've used, I and sum. What are the logics I've implemented? Sum is equal to sum plus I is a logic implemented, and the if statement I implemented, then the I plus plus I implemented. So now we will check whether the program works or not. Now we will execute the program. Now see that how the program now works. Now initialization, I've done it. I finished the initialization. Now first operation. So at the end of the first operation, R2 should get the what? Adding the natural numbers. So now compare. So first time they are not equal. So R3 and R5, they are not equal. So that 0 flag, I'm looking for what flag? I'm looking for a 0 flag. Always you should look at a 0 flag here. So 0 flag is not set. Other flags I'm not interested. So branch, again it will go to where? Again it will go to the continue. See that it has repeated. It has gone to the continuous label. Again add instruction. Now it adds it. Now every time you finish the loop, keep looking at the R2 register. R2 is what? Adding 1 by 1. 1 plus 2 plus 3 like that. Now I'll go to the again. See now again it has come back. Now look at the R2, it has become 3. Now again look at the R2, now it has becomes what? So it becomes a 6. So 1 plus 2, so plus 3, so it becomes a 6. Now it continues one more time. So now it has become A. That means 0 plus 1 plus 2 plus 3 plus 4. It has become A. Now look at the compare instruction. What is the value in R3? R3 has become 5. You're comparing with the 5. So look at the 0 flag here. Now the 0 flag will be set. When you execute that, 0 flag will be set. So that means that, so it is not going to satisfy because it's a 0 flag is set. It's not equal means what? 0 flag should be 0. So it is set. So BE should satisfy, B and E will not satisfy. It will come to the next instruction. So it will come to the stop. So program has stopped. Now where is my answer? Answer is in which register? R2. You can store it in memory also. So now R2 is my answer. So this is how we can implement so the looping of the programs using assembly. So we implemented one. So what is this program? Write a program, assembly program to implement the given for loop. The question should be like this. So, or the question can be what? Write a program to implement the program for addition of the first 5 natural numbers. So now we have understood this logic. Now we'll go to the next program. So now I will remove this program. No. So now we will write a program to perform the addition of 5 natural numbers. I'll modify the, my question is what? So little changed. Am I audible?
Yes, sir.
So now what is that? I have to do program to add first 5 odd numbers. First 5 odd numbers. So we will learn one more small concept here. Now, so I will retain the whole code. So I will retain the whole logic as it is. Only thing is I will change my logic here. Now see that what are the changes required. I have to modify this program to perform addition of so 5 odd numbers. So 5, so first 5 odd numbers. Now see that what are the one challenge you're going to get. Now the I 5 times I have to do it. The 5 times this logic is simple. You require one counter variable, loop variable, which start from 0 and we should go up to 5. This variable is required. But I cannot add directly I here because why? It's nothing but what? The first 5 natural numbers means my addition is different now. First 5 odd numbers means it's my 0. So if I start from 1 plus 3, so plus 5, so plus 7, let's say plus 9. So it comes to be 16, 3 plus 4, 4, 9, 9, 9 plus 1, that is a 10, 16, 16 plus 9, 25. So let's say 25 is my answer. So 25 in hexadecimal is, so whatever the value we will get, we will just see that. So 25, so if I type 25, so and just get hexadecimal, it will be 19. 19 is my answer. Let's see. My answer is 0x19. Now, what is the logic required here now to implement? Since I and the loop variable not related, in this case, directly not related, correct? Now, I will be using one more variable. I will be using one more variable to implement the logic. So j is equal to 0, I have taken it. Now, what I'll do is, so j to start with is what? 1, because odd number start from a 1. And then I'll say that here j equals j plus 2. Now look at the way I've done it. So what I've done, I've introduced one more variable to which is required to implement my logic. And whenever I complete one loop operation, it is required to update the other variable, which is called as j. In this case, j is equal to j plus 2. Because now what will happen? J is always what? j1 plus 3 plus like this, I'll implement. Now, what are the changes required in this program? So, I is required, the same thing I have written, but now there are 3 variables required. So, now I require one more variable to initialize this one. We will see that what is the variable required. So, now move. Now, one more variable is required. R2 is required for storing the sum. R3 is required for this one. Let's say I'll go for the R4, next variable, R4. What is the initial value? 1. Now, this is what you have to identify. When you write a program, identify how many initialization or how many variables are required. The first thing you have to do it. Now, for I require one variable. I've just taken that. Now, I require for storing the sum, one variable is required. I've taken the R2 register. Now, I require one more variable called J to sequence my numbering, sequence odd number generation. So, I've taken another variable called R4. Now, initialization is completed. Now, look at the operation. Now, operation is same thing, add R2. But only thing is, in this case, what will happen? I'm not adding to the. So, in this case, I'm using this. It's for not natural number generation in this case. So, I've used this for R3 for sum, or R3 for loop variable, for I, for implementing the I. So for me, this variable is I variable. For me, this variable is called as sum variable now, R3. So now, so what is this variable? This variable will be, let's say for J. So to generate the odd numbers. Now, so what are the variables required here? Changes required, R2 plus R3. Now, R3 contains the loop. So I don't require R3 here. So what I'll do is I'll just put R4 here now. Because why? R4 contains the odd numbers. So my logic here, so it is changed here. Instead of I, I'm changing it to J here. So now that is what I changed. So sum plus J. So I've changed it to sum plus. Now sum plus, instead of I, it is a J. I finished now. So now after that, so I is, since same, I is nothing but R3, so that I will increment the I one time. I'll compare R3 with the 5. So whenever I want to updation, What is an extra updation required? I have to see that now here. What are the extra updation required? Here, how many updations are required? 2 updations are required. One is I++, which is already there. R3 is equal to R3 plus 1. This is nothing but what? I variable. Now I require J is equal to J plus 2. So one more updation is required. So in the updation segment, add. So what is the variable I have to update? R4, that is J, R4, comma, hash 2. Hash 2. So now 2 updations I have completed here. That is in the updation portion. Now my operation I've changed to sum is equal to sum plus J. I've changed it. Now initialization, I've introduced one more variable for the J. I've introduced it. Now, so now I go to the loop checking whether loop has completed or not. So which is my loop variable? R3, that is I. So which is the same thing, R3 is equal to I5. So now my program is completed. So look at the changes, whatever I have done it. Always increase the or allot the number of registers for the variables required. And then see that how many updations are required. See that what is the logic required to implement your algorithm. So now I'll compile my program. Now my answer is 19 should be there in the register R2 where I'm going to store. Now I'll do one loop first. So now I have finished. Now 1 is there in the R2. Now if I do that, it becomes 1 plus 3. It becomes a 4. Now I'll continue the program. You can complete the program by using what is called as the option called run. So run means it complete the complete loop and stops at the end of the program. So I'll run the whole program in a single shot. After running, you have to stop it. You just stop it and see the value in the R2. 19 is my answer. So 19 is an expected answer. What is in hexadecimal? So that means that the program has worked perfectly. So when you finish the program, so what does so what is the value of R3? R3 is reached 5 because the counter after finishing the program, counter has reached what? The 5. So this is how you can able to implement the for loop with a little deviation. What is the deviation I taken? So in the first case, it was very simple. The loop variable itself was the variable used in the logic. Now what? The variable which is required to implement the logic is different. Loop variable is different. Most of the time, this is the case. This is the type of programs you can take as a reference to implement any logics here. Is it clear? So I'm audible.
Yes, sir.
Okay. So now we will go to another 1 or 2 programs to understand in a better way the implementation of loopings in a assembly language. So now, so I will remove this portion. Okay. So okay. So now I'll go for the other program. So this time I will take a simple program. So to perform the block transfer program to perform the block data transfer. This is very essential in assembly language. I'll tell you why. From code memory to data memory. This is very, very much essential. Why do you require? We know that the data, whatever you store in the code memory at the time of writing the program, I can use that, but I cannot write anything into the code memory. Let's say I've given a set of numbers. I'll given a 10 numbers I've given for you. I will ask you to sort the 10 numbers. So let's say 10 numbers, whatever given to you is there in the code memory. Can you sort in the code memory? No, because sorting requires what? Replacing the numbers at their positions. So whenever you want to implement certain logics and the set of numbers which is there in the code memory, you cannot perform the logics on the data what is there in the code memory because only you can get the data, but you cannot perform the logics. Then what we do, we bring the data what is there in the code memory to the data memory, and then in the data memory, it's like a RAM area. I can able to read and write. I can implement my logics. This is the first step required whenever you want to implement any logics. Now, so we will do the part of that implementation now. What is the part of the implementation? I will bring a set of data which is there in the code memory to the data memory. So what I'll do, I will declare set of numbers, let's say numbers. So DCD in the code memory, 1, 2, 3, 4, 5. So let's say I got a 5 numbers there. I want to bring this to the data memory. It's a very simple for loop you can able to implement. How many times you have to repeat? 5 times you have to repeat. Now, only thing is in this case, so first thing I required what? As always required, initialization is required. So what is initialization required? I have to set up a pointer here, because why? You are accessing something in a memory. So that initialize as a part of initialization, when memory is involved, pointer setting up is important. So always I use R0. So equals the nums. So now I'll get the numbers from the memory, whose name is nums. Now, how many numbers I have to get it? That is 5 numbers. So I will take one variable. So for that, to implement a loop variable, R5, so equals the 5. So 5 is what? It's a variable called I, loop variable. For I is equal to 0, I less than 5, like that I'll be using it. Now my initialization is completed. Now what do I require? Now I have to perform an operation. So in this case, what is an operation? Transferring the data from code memory to the data memory is an operation. So how do we do that one? We have to use LDR and STR instruction. Since you have to require to store something into the data memory also, you require one more pointer. So now, I have just finished my initialization. I started implementing operation. Then I found, oh, there is a requirement of one more pointer. You have to come back. Like this, when you implement any logics, as you start implementing operation, you find certain requirement where you should not declare there only. You have to come back to the initialization block, start adding the other variable which is required to implement your logic. What is the logic required? LDR. So now I'll take one more pointer R1, so which is equals, because data memory is what? 4000 onwards. Yes or no? So that is what 1 GB is a data memory is there. So that I will initialize that value 4 followed by 7 zeros. 1, 2, 3, 4. So this is what? This is the space for area for data or RAM. So this is at 1 GB. So for this chip it is. So now I'll go to the operation now. So first, what is an operation? Get the number into one of the temporary variables. Let's say R2. From which memory? From the code memory R0. I got it. Now, so store this data, whatever you have got, that is you got from a code memory, into where? Into memory pointed by the R1, that is into the RAM area. Now these two instructions is called as memory to memory transfer instruction. First, you cannot do, there is no instructions available to move from code memory to data memory direct instruction. There is no single instruction is available even to move from data memory to data memory itself. You have to always do this through the registers only, through the core only. First get the data into the register, and then from the register you have to move into the memory only. Either code to data or data to data. This is the same concept, you have to use it. Now my operation is completed. Now what is the next operation? So next operation is always called as an updations, as I said. So what is an updation? Update all the pointers, variable, whatever required. So 3 updations are required. I have to make my logic ready for implementing for the next number. So that I have to update pointers R0 and the R1. So I have to update the pointers here. So updating the pointers, what? Add instruction. Always add R0 hash the 4. Similarly add R1 hash 4. Now I updated the 2 pointers. Now what else is required? I have to update the loop variable called I. So which is a variable I have used here. In the R5 I used it. Now, so instead of starting from the 5, I will always start from a 0 here. Because why? I can use a compare instruction. There is 2 ways we can implement it. So if you start with a 5 as a loop counter, you can use instead of compare instruction, subtract instruction. So sub R5, so hash 1 I can do it. Then I say yes. So this is equivalent to compare instruction. I don't require now compare instruction, because why? Since I've used S here, automatically R5, which has got a 5, will be decremented every time 1. So whenever it reaches 0, that means that you have to stop my operation. So sometimes you can use this method also. It left to your convenience. If you want to use a compare, you make it 0 and compare with a 5. So if you want to indicate the number of operation, and then when I reach, I want to stop it, you can use subtract instruction. So I'll go this method in this program. So then branch not equal. So if when I subtract this one, R5, 5 minus 1, first time you'll get a 4, then 4 minus 1, 3. Then whenever the previous answer is not equal, that means it's not to 0, I'll continue my logic. So where is the continue label? Should always go to the operation. Always go to the operation, continue. So now my logic is completed. Now, so let's verify whether we can able to move the data 1, 2, 3, 5 to the data memory called 400. So I have initialized 2 pointers. one for the code memory, one for the data memory. I initialize the variable called I, loop variable. I set it as a 5 because 5 numbers are there. So then I performed an operation, get the number from code memory, stored the number back into the data memory, then updated the pointers to point to the next location. I have updated my loop variable so that can I repeat my loop or not? So this is basically checking for a loop. So loop checking. So this is called as a loop checking. So 4 operations I have given. So now I'll compile my program. So I'll run my program. Now, so there are 2 memories are there here. So we will first execute the one instruction. So nums is nothing but 28 is that. So that I'll just type the 28 there. So my numbers are there. So you can check in the code memory. So in the code memory, 1, 2, 3, 4, and the 5. My data is there. Now what I'll do, I have to move this data into my memory called 400. Now at the beginning, see that no numbers are there. Now I'll execute one by one step. So now what is the first operation? Get the number from code memory and then so move that into here. See that 1 I got it. Now 1 which was there in the code memory, I have moved it to where? I have moved into the data memory. One operation is completed by using these 2 instructions. Now I'll update my pointers. I'll update my pointers. Both the point updated. Now subtract. R5 is what is the value now? R5. 5 is there. Now I'll subtract 1 time. It becomes what? The 4. Since I've used the yes is very important. If you don't use yes, it will not work. If condition will not work. If logic will not work. So now not equal. Look at a 0 flag. I'm looking for a 0 flag. It is not equal. That is condition is satisfied. It will go back now. So now it will go back. It will repeat for the second one. Keep looking on the memory now. So you will get a second number there. Now second number has moved. Now see that third number has moved. Now look at the data memory. So now fourth number has moved. Now keep looking at there. There's a fifth number has moved now. Now look at this one. R5 has reached how much now? R5 has reached 1. 1 minus 1 is what? 0. Keep looking at the 0 flag now. 1 minus 1 is 0. So 0 flag is subtract R. R5 becomes 0. So my 0 flag would have been set here. Subtract sub yes. So it has not changed. So that it has worked, but the flag is not updated here. So I will just run once. The logic has worked fine. So I'll compile the program again. So I will run my program. So I'll execute cpcrsr. Okay. So I'll run my program and then stop it. Now 0 flag is there. I think I would not have compiled after adding the yes there. So now 0 flag is set. So when I finish the BNA instruction, correct now, see that yes, the previous operation is BNA to what? Yes instruction. It 0 flag has been set. It condition is not set. It's come out. Now all my numbers has moved to here. This is how I can implement the logic called as block data transfer, either from code memory to data memory, or the same program you can use it to transfer one area of data memory to another area of data memory. In that case, you instead of nums here, you should take another memory address, which is a part of a data memory. Am I audible? Hello.
Yes, sir.
Yes, sir.
Yeah. Okay. So now we have done 3 programs of the looping. Now we'll go to a little more difficult and useful program. So to implement in the embedded systems. So now I'll go to the next set of program. Now program to add. So set of n numbers, set of n 32-bit numbers. So what is I'm doing? I'm going to now write a program. I'm going to add a set of n 32-bit numbers. This is very essential. This is the basis to find out an average. For example, you developed a small embedded system and deployed that embedded system in a remote area or a greenhouse or some place where you want to monitor the average temperature in that place. So what you do, you can give a small microcontroller with a temperature sensor. Every 1 hour, it measures the temperature and store it in a RAM. So at the end of the day, maybe 24 samples you have. Even you can make it 1 minute also, because you have a lot of memories there. 32 kilobytes of RAM is there. Every 1 minute you can able to get the temperature, store the temperature in a RAM. Once you've finished your program, once you've finished complete your program, then what you can do, once you finish the day, at the end of the day, what you can do is you can add all those temperatures, and then divide the temperature by the number of readings, whatever you have, find out an average, and then send to the cloud, the ThingSpeak cloud or something like that. Then what will happen? You don't require a lot of data usage for communicating from your embedded system to the cloud. Basically, I'm interested to find out what is an average temperature, maybe the maximum and the minimum temperature in a particular place, in a locality. Now, this is called as edge computing. We use a word called as an edge computing. Edge computing in IoT, a lot of thinking, a lot of work is going on. What to calculate? What is the work you have to do at the edge level, that is your embedded system? What is the work you have to do at the cloud? You may say that I can push all my data every 1 second to the cloud. I can do it, but you have to pay money for the cloud updation. You require a lot of data usage. So the investment will be more. What is the best model is whatever possible, you have to finish execution at the edge devices itself. That is at the place where you install your equipment. Only when you derive the perfect answers, that means you got the insights out of your data. That what is the insight? Average temperature, maximum temperature, minimum temperature. That is the insights. Those insights you have to capture that and send once in a day. Then what will happen? So that is a most economical model, and most system is more efficient. So for that one logic, what is the logic required? To add the set of n numbers is required to implement that big program. So I'll be doing one portion of that now. So program to add a set of n numbers. So we'll make it a simple case first. Then we will see what are the shortcomings in the program, and we will try to correct it. Now, where is my n numbers? In this case, I can keep my numbers in the code memory and add it and store my answer in a register. So I'll take a simple case. So, or if you want, you can feed the data at the runtime in a data memory and then feed your numbers, and then you can do that also. So we will take the other case. So we will take the data at the runtime in a data memory. Now, so to start with, so I will always start with what? Initialization. What are the initialization required? I require a pointer to get the data from a memory. So I'll use R0 always. R0 equals, since I'm using at the runtime the data present in the memory, whenever you want to use the data at the runtime, you have to use always what memory? Data memory. That is a RAM area. So 0x4 followed by, okay. Now my memory is there. Now what are the initializers required? How many numbers you want to add it? So for that, one index variable is required, loop variable is required. Let's say I'll use R5 always. So move R5 hash, let's say 5 numbers I have to add it. Now I require one more variable to hold the sum of all the 5 numbers or 5 temperatures. So I require one more variable. So let's say I'll be using the R2. So I'll initialize to 0. Now this variable is for what? So sum of temperature, sum equals 0 I implemented. So this is nothing but what? So 5 times 5 numbers I have to do it. So that means that loop for it's an I variable. It's an I variable. So loop for 5 times. So loop for 5 times. So now, so this is the memory pointer. So memory pointer. Now, so my initialization is over. Now I'll start with an operation. So what are the operation I'm supposed to do it now? So operation is what? I have to get one by one number into the register from the memory, add to my sum variable. How do you get the data? We know that it's nothing but what? LDR. So get the data into one of the variables. So let's say R1 variable, R1. Now my point is what? R2. So now I got the number into first number into my register. Now I'll add to that sum variable, add. So sum variable is nothing but R2, comma R1 added. Now my operation is completed. Now what is the next step required? Always is what? Updation of the variables and the pointers. So what are the variables I have to update? Now pointer you have to update it. So now add. So what is my pointer? R0. So make sure that it will point to the next location, next 32-bit location, next temperature. Now I have completed one time the loop. So that what I'll do, I can subtract R5 with 1. I can decrement the value by 1. So this time what I will do is, instead of implementing this logic, I will implement the other logic. So I'll use a compare instruction to make it convenient for you so that you can use that or this. Now updation, what are the variable I have to do it? Add now R5. So 1. That means that one operation is completed. One time loop is completed. What is when I say R5 is equal to 1? That means that I made it 0. When I added 1, that means that what? So it's nothing but what? It's nothing but I is equal to I plus 1. So now I have completed one time operation. Now check for the loop completion. So check for loop completion. Loop completion. Now what should I do it? Now I have to compare here. Compare R5 with a 5, hash 5. Instead of subtract instruction, I use compare instruction. You can use always anything. Now what I have done? So I'm checking whether R5 is equal to reach to 5. So if not, so branch not equal, so continue. So I've implemented if the loop is not completed, it's not reached the 5. So it's nothing but I less than 5. I'll go back to here. What is on a place I have to go back? That is an operation. So continue. So I'll come back here. So now see that my logic has completed. I've used one pointer and two variables, one for the sum, one for the loop variable called I. So I have performed an operation. I got the data from memory, and then I've added to R2, that is some variable. So then I updated my pointer and I updated a counter variable, a loop variable. Now check for whether the loop variable has reached 5 or not. So now I'll compile this program. At the runtime, I'll feed the data. Now, no errors are there. Now I'll go to running my program. Now, so at the runtime, whenever you perform this operation, at the runtime, you have to feed the data. That means that before running your program, feed the data here. So now let's say I have given a simple number. Let's say 1, 2, 3, 4, and 5. These are the 5 numbers I have given it. So that is 3, 6, 6 plus 4, 10, 10 plus 15. That is 15 is my sum of these 5 numbers. 3 plus 3, 6, 6 plus 4, 10, 10 plus 5, 15. That is sum is 15. The answer should be F. So these are the 5 numbers I'm adding it. So these 5 numbers will be adding it and storing my answer in which variable? I'm storing in a variable called R2. I'm just storing in R2. You can move that into a memory location also. Any of the location. For example, 40000, 5 you can use it, or 4000010 you can use it. Like that you can use any other memory location to store the answer also. In this case, I have stored my answer in the register. Now I'll execute the first loop. So I'll see that the first answer is correct. So add R2. See that R2 has got, no, it's not correct. So some mistake we have done it. See, R2 has become R1. What is the value in R1? So R1 is changed. So what is my R0? So R0 is 40 is correct, but the value what you got it here is a wrong. So what I have to do it? I have to stop my program here. So I'll check again I'll compile my program one time. So there's a one mistake is there.
So while dynamically loading, you had given it's a 32-bit number.
Yeah. So I have to increment that by one pointer, but I have to change the numbers. Okay. Yes. Very good. So what I have to do is, so my program is correct. My feeding of the data is not proper. So that 1 is here. So I will, the first number is here 1, then 1, 2, 3, 4. Then the second, then this is 3. Then this is the 4. And this is my 5. So thank you very much. So now what I have done, I have stored my 5 numbers as 32-bit numbers. So 1, 2, 3, 4, and 5. So now I'll get my first operation. So I'll see that R1 I got it, 1 I got it, then finish. So now R2, look at the R2. Now R2 is nothing but 1 is there. So I'll finish one more round. So I'll finish the second operation. It should be 3. So that my logic is continuing. Now I'll run till the end and stop my program. Now what is there in the R2? F is there. That means that addition of the 5 32-bit numbers is answer. I've got it. So this how I should able to implement my logics of which is nothing but a for loops in a assembly language. One small correction we will make it here. That is to make it a complete 32-bit numbers, complete addition of n 32-bit numbers. Let us take an example here. Now let's say I have a numbers. So whenever I want to add the numbers, for example, I will take a decimal number system first. I'll give a 10, then I'll give a 99, then I'll give 85. Like this, I've given a set of 2-digit decimal numbers. What is the method you follow? First, you add 10 plus 99. So what is a 10 plus 99? So 10 plus 99 is what? So it is nothing but 9 here. That is my answer in this case when I add it. So 9. Then I'll add 9 plus 1, that is 0. Then I'll have what is called as carry of 1. Next, I'll go for, now these two I finished. Now I have got a 09 is there. Now I want to add the 09 to the 85. So now adding 85 to the 09. So now what is there? I'll be adding 85 for this. Now what is my answer? So now my answer is, so 9 plus 5, that is 4. Then so carry of 1 here, that is 8 plus 1, that is 94. Now, so whenever you add a set of numbers like this, in between when you're adding, you get a carry. So if you neglect the carry, at the end, if I ask you what is your answer, if you say only 94, your answer is wrong. What you have to say? 94 plus you have to say what? 1. I'll consider one more number. Let's say I've added. That is one more number is there. One more number. Let's say it is 74. 74 is my another number. So what I'll do now to this 94, I will add the 74 now. 74. Now my answer is now, so 4 plus 4, 8. 4 plus 4, 8. Then 9 plus 7 is what? 16. That is a 6. And then carry of 1. This carry, whatever generates, you should not make it 1. You should add to the previous carry, whatever already there. So how much it will be? 2. Now, so now look at this. Now, whenever I add two numbers, what I do, first add them. If the carry is there, I'll store it in one variable. Next, again, I'll add another number to that answer, whatever you got it. If the carry is generated while adding it, what I'll do is the carry will be added to the previous carry. So that means that at the end of the program, if you say 68 my answer, it's wrong. What you have to say? 02 plus 68 is my answer. So this logic, I have not taken consideration in this one. Because when I say set of n 32-bit number, 32-bit number can be very large. Say, for example, if I take the FFFFF is one number, another number is also FFF, then what will happen? When I add the two numbers, carry is generated. I have not taken care of accumulating the carries and the end giving my answer as what? Two 32-bit numbers. Actually, answer is what? Whenever you add two, for example, in decimal, when you add 2-digit decimal number, what is your answer? Your answer is always what? 4-digit decimal number, because 2 digits represent the one part of the answer, another 2-digit represent what? Accumulated carry. Similarly here also, when you add a set of n 32-bit number, what is your answer? Answer is always 64-bit number. So the first 32-bit number represents the lower part of the answer. The next 32-bit number represents what? Accumulation of the carries. So I will modify this program to include that one, and also I'll feed the numbers a larger numbers now this time. Now, so whenever I finish my addition, always I should do what is called as one checking. What is the checking? Is when I add two numbers, is the carry is generated? This carry is generated. I have to check for that. So I have to do here. So whenever I add, if at all if the flags has to be changed, because I am interested in the carry, you have to add what? Number 1, you have to add yes for this. Now, so I will take now one more variable, because you want to store the part of the answer. The sum, that one register is not possible to store the complete answer. I will require one more register. Since R3 is not used anywhere here, I use another variable called R3. Move R3 hash 0. I'll make it 0. This is what? To accumulate the carry, to accumulate the carries. So every time you should add 1 to this R3 register whenever you get a carry. To begin with 0, I'll make it. Now, whenever after perform the addition of two numbers, if at all if the carry is generated, I'll add 1 to the R3. How do I do it? We have we know that in the last class we studied what is called as conditional execution enabled instruction. That is, instruction can be suffixed with a condition code. What is a condition code? If the carry is set, that is carry set CS. So we know that we have studied yesterday. So there is what is called as flags there. What is called carry set and the carry clear. Two flags there. I'll use CS carry set. So now I'll come here. CS, I'll use it. CS carry set. So that means that if at all, if the carry is set in the previous operation, I will increment R3 by what? 1. I'll increment R3 by 1. Now my program is completed. This program is what? Now it's completed. There is no error in the program. You are not losing any data in this program. Now, when you run this program, where is my answer is stored? Answer is stored in two registers. R2 is an LSB 32-bit. R3 is what? MSB 32-bit. It's similar to whatever I do in the decimal addition. You require, so one register for this, you require another register for the upper part of the answer. Now we will run this program. So I'll make this statement. So now I'll compile my program and see that I'll feed a large numbers and my program works or not, I'll verify it. So last 2 minutes. So
sir, I had a doubt. What is the difference between add C and add CS, sir?
now ADC is the add with a carry, whatever there in the previous one. Yes or no? I am using a conditional execution instruction. You can use add C also for this one. You can use add C also, because if the carry flag is there, so we will try that also. Huh? So both you can use in this case. So now I'll feed my numbers here. I'll feed a large numbers now. FFF. So FFF, 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 FFF. The second number also I'll make it bigger one. So other numbers I'll keep the same numbers. So now. So 1, 2, 3, 4, 1, 2, 3, 4. So other numbers, let it be zeros. So now what I've taken two large numbers, 1, 2, 3, 4, 1, 2, 3, 4 FF. I'll take one more number. So I'll take some large number. So FE and something called 10. So other numbers are 0. So totally 5 numbers are there. First number I taken FFF, second number FFF, third number is what? FFFF, FE and 10. Other numbers are 0. So now I'll execute my program step by step. I'll see that. So now I am adding the first number. So I got the first number. So what is on first number? So first number is in whatever I got in R1 is a FFF. I got it. Now I'll add this first number. So now for the first time R2 becomes FFF. Now the carry is not set because first number is what? It was a 0 first time. So now I'll continue the loop. Now compare. So now I'll go to the second number. I'll get the second number. Now look at the second number. Second number is also FF. The first previous sum is also FFF. When you add these two numbers, carry 100% will generate. Look at the carry flag here. So now the carry flag is set. Now in the previous operation, this R3 has not incremented. Look at R3. R3 has not incremented because why? Carry was not generated. Now with this time carry is generated. So what will happen? The R3 is incremented because it's a conditional execution instruction. See that R3 has become what? 1. Now what is your answer? Answer is R3, that is 1, and then R2 is an answer. The both will constitute an answer. I'll finish the execution and stop it. All the 5 operations are completed. If somebody asks, what is your answer? Now R3 that contains a 2 because 2 times the carry is generated, and then whatever the value in R2, 10, FE, FFFD, this is the answer. So this is the way you can able to give a perfect 64-bit answer when you add a set of n 32-bit numbers. So this is about the completion of this program. You can always I'll just stop that recording and tell you that you can always use ADC